So today we are going to introduce the diffusion. Actually, diffusion is very important thing with respect to metallurgical and materials engineering. Chemical industry also, metallurgical industry also are very much relying on the diffusion process. Lot of things, heat treatment process. If you are looking at the heat treatment of steel, if you are looking at the phase transformation, if you are looking at the doping or creep mechanism at the high temperature deformation, all those things are highly dependent on the diffusion process. So in order to understand the underlying physics of materials engineering sector, one should very thorough about diffusion. So today we are going to understand which are the sector, taking certain example, are very important with respect to governed by the diffusion process. So let's see the history of the diffusion concept. Fourier, Joseph Fourier in 1822 modeled how a quantity such as heat diffuses from one portion to another portion through a given region. So he tried to model that and he formulate with respect to certain criteria of mathematical understanding of the process. Then he tries to get the real physics behind the heat diffusion. If that time he used to tell that one quantity as heat diffusion from a given region through a given region. Then 1855, Fick, well known to us that Fick's law of diffusion, he actually introduced the Fick's law of diffusion in 1855, which governed the diffusion of a gas across a fluid membrane. At that time, he actually was concentrating on the diffusion of a gas across a fluid membrane. After that, in 19th century beginning, 19 more specifically 1905, Albert Einstein related the diffusion constant to the physically measurable quantities. You can name that mean square displacement of a particle in a given time interval. Einstein analyzed the dynamic equilibrium established between two opposing forces. So Einstein then tried to understand how particle physics, based on the particle physics, how mean square displacement of a particle is related to the diffusion constant. And that kind of concept introduced by Albert Einstein in 1905. So then onwards, the things are slowly evolving regarding the diffusion process. Chemical potential concept came and people are understanding diffusion much more clearly. Now things are still, there is certain gray areas are there. People are doing research on the solid state diffusion, stress induced diffusion. So things are still very vibrant with respect to research area in diffusion. Now, in materials engineering sector or metallurgical industry, what are the different things are really rely on the diffusion process? We are not going to concentrate on such kind of cases, taking certain examples. So let's start with phase transformation. So here you can see how to understand a phase transformation process. Previously, I told that any process, there is a two things. One is feasibility criteria and another is process is operational. So one will be known from the thermodynamic understanding of the process and another one, second one will be known by kinetic understanding of the process. So diffusion is a movement of atom. So it's a dynamics is there from one part to another part. Certain atom is moving, and then the diffusion process is involved. So that is going to relate the kinetic part of the process. So feasibility, it's always related to the Gibbs free energy or free energy minimization. And if you are look at the kinetics, then you have to go for rate equation and all those things. One example, that is austenite to pearlite transformation. So you can see the pearlite growth direction is there. Now, to start this example, first we should know what is phase. Phase is physically distinct, chemically homogeneous, and mechanically separable part of a system. Then we should brush up our knowledge about the system. There is the three kind of systems: isolated system, open system, and closed system. So in the, even if you go for more general statement, then you can tell phase is a part of universe which is physically distinct and chemically homogeneous and mechanically separable. So here, if you see, the austenite is the initial phase. Slowly, the parent phase austenite, it transforms to the perlite. And what is perlite? Perlite is a mixture of ferrite and cementite. And this is also two different phases. Now, how this process is occurring? The most important part is that carbon diffusion is actually governing the phase transformation from austenite to perlite. So you can check that growth of perlite from austenite actually depends on the carbon diffusion process. So these things is actually revealing, this is revealing to us that there is a strong contribution of diffusion process in phase transformation in materials engineering sector. So as a whole, what we understood, that phase transformation is dependent on the diffusion process. If it is a diffusion control phase transformation, there is a certain diffusionless phase transformation we are going to come across when we are learning the subject of materials engineering, like martensitic transformation. But here things are very important, that what is the, when we are talking certain phase transformation is a diffusion control phase transformation. When the phase transformation is taking place due to movement of atoms with respect to its initial position, multiple of lattice parameter. Is a multiple of lattice parameters when his atom is moving with respect to his initial position, then you are going to tell that, and new phase is generated, then you are going to tell that it is a diffusion control phase transformation. And in practical purpose, if it is a heat treatment process, it is required to enhance the property, sometimes customize the property, application specific property. If you want to incorporate in particular material or metal alloys, metallic alloys, then you have to go for heat treatment. And heat treatment process is, it's directly linked with the tune the microstructure in order to achieve desired properties, mechanical, physical, chemical, or you can tell magnetic properties. So for that, phase transformation is very important part. Certain phase has certain properties. The contribution to the final properties of the metal, certain phase contribution are having certain different approach. So that is the important things, that phase transformation is required to be done, and due to diffusion control phase transformation, we can tell that diffusion is important phenomena we should consider. Now we are going to understand the carburizing part. That is another phenomena. It is a very practical things. Actually, if you check any gear of a any industry, if you are using gear, then always people very concerned about the wear resistance as well as the toughened core is required to get the load and to withstand the load. What is, so the requirement is like that. It should be the very toughened or soft core and hard surface is required if you want to get a gear kind of product. And for that, low carbon steel will give you the toughened kind of things, is ductility will be high, but the wear resistance will not be so high for the low carbon steel. So for that you have to go for surface hardening process, and carburization is one of the most important surface hardening process for low carbon steel. And what it is, carburizing is the addition of carbon to the surface of the low carbon steel at high temperature. You can tell that generally the temperature between 850 to 980 degrees centigrade, at which the austenite with its high solubility for carbon is the stable crystal structure. So now things are very simple. What we are going to do, through the certain temperature, we will reach the austenite phase, and then we are trying to incorporate the carbon inside the austenite phase. What is the low carbon steel, what is staying in the surface of the product. So one should ask the question that why austenitic temperature one should reach, but why high temperature is required, like 850 to 980 degrees centigrade, where austenite the phase is stable. Why you are looking at that? Because austenite, although it is a FCC crystal structure, it is having higher carbon solubility with respect to ferrite, which is low temperature stable phase for steel. Ferrite having less capability with respect to solubility of carbon in it. But if you check the atomic cracking fraction, BCC iron and FCC iron, you will see that FCC iron is more close packed. Still, it can accommodate higher percentage of carbon inside it with respect to BCC. This is a very tricky question. That you are having more vacancy places in BCC, but still the capability to dissolve carbon in it, it is not so high. But if you look at FCC phase like austenite, it is having higher capability to dissolve carbon in the lattice. How is it possible? Now, in order to understand that, you have to understand the interstitial position and what is the void shape. If you look at BCC structure, more number of voids are tetrahedral voids. But if you look at FCC structure, you will get more number of octahedral voids. And if you compare the shape of octahedral and tetrahedral voids, then you will understand that octahedral voids are more symmetrical voids with respect to tetrahedral. It is asymmetrical voids. So putting one carbon in the interstitial position of a FCC phase like austenite, it is create less elastic strain imbalance, because it going to get the position inside the octahedral voids. That octahedral voids are symmetrical voids. So in symmetry voids, the elastic strain will be and asymmetry nature will be very less. So stability, with respect to stability of the structure, the contribution will be high. So that's why austenite can accommodate more percentage of carbon. And what you want in the carburizing process, you want that surface will have more carbon inside the low carbon steel, so that low at surface the steel will be hardened, because carbon solubility of a steel in a steel, and then if the carbon percentage in the steel is increased, then the hardness will be enhanced, as well as the wear resistance of that particular position of steel will be enhanced where the carbon percentage is high. And there are different methods are there: pack carburization, gas carburization, liquid carburization, vacuum carburization. And all the cases, if you see pack carburization, the nature of case is diffused carbon is important. And if you gas carburization, there are also carbon diffusion, but the process will be different with respect to the material where you are taking. The pack carburization, state diffusion will take place. If you look at the gas carburization, then carbon monoxide and all those things, gases are used. And this carburization process is required very good amount of diffusion of carbon inside the surface of the particular product made by low carbon steel. So in this way, what you are achieving? You are achieving hard core, soft core and hard surface. So you are achieving the wear resistance at the surface as well as the toughened core, ductile core, so that your failure will be delayed. So that is one thing. This is also good example of how diffusion is very strong or significant factor for metallurgical process or materials engineering process. Now we are going to understand how diffusion is important with respect to oxidation. If you see, corrosion sometimes is due to certain kind of reactions. So it is basically reaction process is going to take place. And oxidation, if you put silicon and in a atmosphere or in oxygen atmosphere, then it will oxidize to silicon dioxide. And this oxidation process is required diffusion from surface of that silicon block to inside movement of the oxygen through the channel. It can be voids, it can be vacancies. So this kind of movement of oxygen is important. This kinetic factor is important to understand how oxidation of particular metal is going to happen. Rusting of iron is one of the good example of that. That's that kind. So this thing that diffusion also playing some certain roles with respect to deterioration, corrosion, and oxidation of metallic system. So that part is important. Their interface, how oxygen is going from the interface, in this case, it's the surface of that particular metal to the inside the metal and make the metal oxidized so that oxidation can occur. So diffusion is important. Now we are going to understand with respect to sintering process, how diffusion are playing a significant role. If you want to understand that, then you have to know what is sintering. Sintering is an agglomeration process and through which incipient bond is forming. Fused bond means in localized contact of two particles, there will be a certain fusion. That incipient fusion bond can form. Incipient means that if you check in the picture, there is a certain kind of localized contact. In the contact of two particles, certain localized plastic deformation, or you can tell certain small kind of melting or localized diffusion or localized bonding can be formed. Now, what are the different mechanisms are important or are dominant with respect to sintering process? If you look at the picture, the particle, inside the particle, there is a volume diffusion can occur. And when you are talking about if it is a metallic particle, there will be a dislocation phenomena can occur inside the particle. And in the picture, there is a one edge dislocation. One drawing is there. If you look at the bottom particle, and there is a, if you then, when the particle is contacted in another particle, it looks like a grain. Then you can, through that interface, or if you certain diffusion is occurring, you can tell that this is a grain boundary diffusion. And the surface of the particle, there is also movement of the atoms can be there. That is surface diffusion. So when the sintering process is occurring, then surface diffusion, volume diffusion, grain boundary diffusion are relevant, are dominating. And since these are the dominating, that may cause the plastic flow of the material in the particle of the interparticle plastic flow. And that actually makes the sintering process done. So this is the important phenomena, that diffusion is important with respect to sintering process also. Now we are going to look at doping, how doping is governed by diffusion process. First, why doping is required? In electronic industry, to designing the electronic materials, doping is very relevant thing. PN junction, diode, triode, the junction, all those things, electronic circuits material, if you want to create integrated circuits, the doping process is very important. And generally, doping of semiconductor are very popular and well known. So now we have to start with the scenario. What is semiconductor? Semiconductor, there will be a very small band gap between conduction band and the valence band. So you can tell that semiconductors are not intrinsically conductive. They are not intrinsically conductive. So make them conductive, what we can do? We can replace the silicon atoms in the lattice with the dopant atoms that have valence bands with fewer or more electrons than the silicon, that is 4. So if more electrons is there, then the dopant will become a donor. You can take the name phosphorus, arsenic, all those things, and the extra electron is effectively released from the bonded atoms to join a cloud of free electrons, free to move like electrons in a metal. So we are getting the conducting medium, that is a free electron. So doping is very important to enhance the conductivity of a semiconductor if it is required. And if you want particular way of particular carrier of the conducting process, you can design as per the selecting the dopant. So how doping is happening? If you check in the picture, that when on the surface and certain temperature, slowly dopant atom going inside the substrate. So this is also this is also indicating that the diffusion is very important with respect to doping process. If you don't want to design MEMS and all those things, lithography, etching, all the area doping is all those area of diffusion is very important phenomena. So understand the diffusion process is very important. And there is lot of things, substitutional kind of diffusion, interstitial C or interstitial diffusion, all those things, atomic scale mechanism we'll understand as we progress in this subject. Now we are going to understand the creep process. What is creep? In textbook definition, it is like that: high temperature deformation at constant load. Now, lot of question will come. Why high temperature deformation we are looking at? Why that can be constant load in the low temperature also? Why high temperature? Because high temperature deformation process is becoming complicated. Low temperature generally dislocation mediated diffusion, deformation process are dominant. But at high temperature diffusion also important thing, and diffusion can be taken care of lot of things. Suppose how diffusion will be contributory and how strongly can govern the creep process depends on the temperature of the diffusion, temperature of the creep process, as well as the structure, microstructure of that particular metallic system or alloy with respect to grain size. If the nanocrystalline grains are there, then what is going to happen? Nanocrystalline means the one grain, one dimension must be less than 100 nanometer. So very small grain size can help you to get high strength as per the criteria of decreasing the grain size. You are getting high yield strength up till certain as per the Hall patch equation. But at high temperature, what you are getting? High volume of grain boundary. And if it is beyond equicohesive temperature, then what is going to happen? Grain boundary is weaker than grain. So if that revision of temperature, if deformation is occurring, then grain boundary diffusion, lattice diffusion, all the process are going to play a very strong role. And then the creep deformation process at very high temperature are really governed by diffusion process. People used to name that diffusion creep. Navarro herring creep and cobalt creep, both are under diffusion creep. Navarro herring creep is talks about lattice diffusion, and cobalt creep it talks about grain boundary diffusion. Now we can understand that creep process is also depends on the diffusion process. Diffusion is very important in order to understand creep. In particular, if it is the nanostructure or nanocrystalline material you are talking, then you have to very serious about diffusion process taking place in the metal or materials. Now we are going to understand how diffusion bonding. Then you can see in the actual process, diffusion bonding, diffusion what is there. So the bonding is taking place due to the diffusion process, and that can be done through the stress induced diffusion. You can tell it can be two base material in between the one interlayer. If you see the picture, then you put a certain pressure both side and try to get the diffusion process activated. And for that, if the interlayer is so pure and the surface contact will be very good, through that contact surface, diffusion can take place and create a bonding, that is a joining can take place, that is named as diffusion bonding. So these are the few examples I have taken in order to make you understand that how diffusion is very important for materials engineering sector. Now, simple way you can understand one most fundamental process that governs the rate at which many transformation of materials and material technological process occur is the diffusion. Now we have to believe it. Till now, whatever discussion we have done based on that first sentence of this slide is acceptable and credible to us. Now diffusion, now what is diffusion? Diffusion describes the spread of particles, which can also be atoms, molecules, through random motion usually, but not always, from region to higher concentration to regions of lower concentration. It is written. Now there are 2-3 catches are there. Spread of particles, which can also be atoms and molecules. Okay, then atomic diffusion, atom molecule level diffusion is going to occur. It is acceptable. Through random motion. So if it is through random motion, and also you are talking about the governing factor is the concentration gradients, means region of higher concentration to region of lower concentration things are going. So concentration gradient also a governing factor. Again, you are telling the random motion. So both things are appear to be a contradicting. How to understand that? The random motions here it is telling that it is not going to take place a particular path from one position to another position. It will go through the process where there is a vacancy, there is a options. So that way it will go. Okay, channelized diffusion also one concept, but later on we'll understand. So through the random walk model, generally diffusion process is described. Now one bracket, one word is there, but not always. Means always you cannot tell that higher concentration to lower concentration region the diffusion will occur. Maybe reverse can be possible. Already we understood that thing from miscibility gap or concept of miscibility gap, where pure become more purer. So then what is happening? Then we can tell that not higher concentration to lower concentration, but higher chemical potential to lower chemical potential, but that may be higher concentration to lower concentration. And we can tell this kind of exceptional diffusion process named as R-field diffusion. R-field diffusion. What is R-field diffusion? Again, I am repeating. When diffusion is occurring due to chemical potential gradient and reverse off to the concentration gradient, means higher chemical potential to lower chemical potential materials is moving, but simultaneously the scenario is like that lower concentration to higher concentration things are moving, the material is moving. So that is the thing, and that kind of things you can see in the miscibility gap. Thermodynamically I have discussed this thing. Now that behind this kind of phenomena, the R-field diffusion is important. So not always that you can tell that from the regions of higher concentration to regions of lower concentration will go. So, but not always, that word is very important. So whenever you are defining one concept, here we are defining diffusion, we'll be very careful about choosing and selecting the technical words. Each word are very important. Now we are going to look at one cases. That one side, if you in the picture, you can see one side is A rich, another side is B rich. So A rich to B rich, both are come to contact. So A rich to B rich, the A will move, and B rich to A rich, B will move if they are coming to contact. So here what we are looking at, the time dependence of the statistical distribution space is given by diffusion equation. We know that there is a lot of equation later on we'll understand. But the concept of diffusion is tied to the mass transfer driven by concentration gradient. But diffusion can still occur when there is no concentration gradient. Suppose there is no concentration gradient, means you are taking a pure metal and you are heating up, and then also diffusion is taking place. So where you are going to get the concentration gradient? What is the governing factor for the diffusion? What is the role here? Then you have to understand the perturbation theory. That each atom actually is in its position is vibrating. So there is always a fluctuation. And due to fluctuation, you can tell that local density difference will be there. Local clustering of an atom can happen. That create a scenario that fluctuation, perturbation helps to get the diffusion process. So for cell diffusion, we used to then looking at high temperature. Why high temperature? High temperature actually leads to the vibrational kind of fluctuation more. What we understand from concept of CP also previously. So that way. Now look at this phase diagram, A and B. And there you are seeing that one plot is there. And when the things are coming, GM is decreasing. GM is that from the line G2 and G1 connect and actual the free energy diagram of that particular phase, that is the mixing. Already we have gone through this kind of phase diagram. We understand that. Now we are looking at that how chemical potential is very important in order to get the diffusion process. So here the connection of thermodynamics and kinetics. Here the diffusion process is depends on the chemical potential gradient. There you can connect both things. The chemical potential also can be defined based on Gibbs free energy and entropy concept. Now diffusion, now we have understand diffusion is always along chemical potential gradient, not concentration gradient. Although Fick's told that, but Fick's after that lot of advancement is there. So Fick's law is not always valid. If you talking about field diffusion, then you have to be very careful about that. And when the now you see the Gibbs free energy is curve is different. It is looks like a mostly this kind of Gibbs free energy curve we came across for the visibility and all those things. Here you can see the how the chemical potential is more important, and actually it is the governing factor if you are comparing with concentration gradient. So now onwards from this class, we always define diffusion with respect to chemical potential gradient, not by concentration gradient. Because based on concentration gradient, the diffusion equation is fixed concept, but that concept is not always valid if you look at miscibility gap or aphel kind of diffusion process, mainly aphel diffusion process. So you have to understand that. Now here I try to correlate how isomorphous phase diagram, the Gibbs free energy diagram, and then how it is related to the actual concentration curve. Low angle tilt boundary A. Okay, because this low tilt boundary, gain boundary, all those concept is different. It's a part of the gain boundary engineering and all those things. Forget about that. There is a two side. One is A rich, one is B rich. That way you can start. And imaginary AB isomorphous phase diagram. If you look at Gibbs free energy that G star, and then chemical potential of the component is different, composition different. And if you look at the D curve, that slowly that composition will try to a scenario where the gradient will be minimized. That is the driving factor, kinetic driving factor for the process. for the diffusion should be gradient will be minimized. Here, what is the gradient? Gradient is, we are talking about chemical potential gradient. Now onwards, always we will concentrate on chemical potential gradient in order to define diffusion process. Thank you. So today class is completed.